Okay. So, hi everyone. So, good afternoon all. So, I hope audio and video everything is clear. So, if it is not clear, please comment in chat box here, right? Okay. Okay. So, we are dealing with the subject electromagnetics, right? Okay. So, we have completed magnetostatics here. We have completed magnetostatics part. So, in magnetostatics part, we have studied Lorentz force equation and its applications, and then Biot and Savart's law and its applications, and also we have studied Ampere's law and its applications. Yes or no? Okay. So, we have completed magnetostatics, right? So, next, so next topic is time varying fields here. So, next topic is time varying fields. So, next we will start time varying fields. So, in this time varying fields, we are going to study about Faraday's law. So, the first one is Faraday's law. So, and then we will study modified Ampere's law. So, after this we will study modified Ampere's law, right? Okay. So, these are the basic two laws which leads to what? Which leads to the discovery of electromagnetic waves. Okay. So, we will see that conclusion later once we complete these two laws, right? Okay. So, today we will start with Faraday's law. Today we will start with Faraday's law, right? Okay. Okay. So, we will start with Faraday's law. Okay. Okay. See here. Faraday has got one doubt here. Faraday has got one doubt. So, what is his doubt is, we know that whenever you are having a current, it is going to produce what? It is going to produce B field, right? Okay. Now, Faraday has got one doubt, that is whether this B field can produce what? Can produce the current or not. So, this is the doubt who got here? Faraday. So, we know that the current is going to produce what? Whenever you are having current, it is going to produce the B field. Now, Faraday has got one doubt, that is whether this B field can in turn can produce the current or not. So, this is the doubt Faraday has got. Okay. So, whenever they will get doubts, what they will do here? They are going to conduct some experiment. Yes or no? So, our Faraday has also started conducting some experiment. So, what he has done is he has taken a conducting loop here. He has taken a conducting loop like this. Okay, and at the ends of the conducting loop, he has connected a galvanometer. At the ends of the conducting loop, he has connected a galvanometer, right? Okay. So, what is the purpose of galvanometer here? So, the galvanometer can be used as either what? Either ammeter, or it can be used as what? Or it can be used as voltmeter. So, galvanometer can be used as either ammeter or voltmeter. Understood? Okay. So, he has taken one conducting loop, and to the ends of this conducting loop, he has connected a galvanometer, and the purpose of galvanometer is it can be used as either ammeter or voltmeter. Right? Okay. Okay. So, then what he has done here is he has taken the magnet here. He has taken the magnet and kept that magnet near the loop, near the conducting loop like this. Okay. So, he has taken the magnet and kept the magnet near the conducting loop, right? Okay. So, why he has kept the magnet near the conducting loop here? But because he wants to know whether this B field in turn can produce the current or not. Okay. So, whenever you place a magnet here, what will happen here? It is going to produce what? It is going to produce, or it is going to set up a B field. Yes or no? So, that magnetic field lines are going to penetrate through this loop, right? Okay. Okay. So, if suppose if suppose this B field, if suppose let us assume if this B field produces some current, then what will happen here? So then if this B field induces some current in the loop, then what will happen? This galvanometer is going to show some deflection. Understood? Okay, so that's why he has placed this conducting loop, and at the ends of the conducting loop he has connected a galvanometer, and near this conducting loop he has placed a magnet. Understood? So this magnet is going to produce what? Is going to produce some magnetic field lines, and that field lines are penetrating through this loop, Understood? Okay, okay. Yeah. So now so now he want to know whether this B field is going to induce some current in the loop or not. Understood? If at all it induces some current in the loop, then the galvanometer is going to show some deflection. Right? Okay. So he kept the magnet like this, and he has waited for 1 hour. Still there is no deflection in the galvanometer. So 2 hours completed, still there is no deflection. 3 hours completed, there is no deflection. Understood? Okay. So then with a huge disappointment, what he has done is he has taken the magnet away from the loop. So whenever he has taken the magnet away from the loop, he suddenly observed a deflection in the galvanometer. So whenever he has taken the magnet away from the loop, suddenly he has observed some deflection in the galvanometer. So then again what he has done is he has taken the magnet again nearer to the loop. So whenever he is taking the magnet again nearer to the loop, in that case also he observed the deflection in the galvanometer. So then he started playing. So he has taken the magnet nearer to the loop and away from the loop, In both the cases here, whenever he is moving the magnet nearer to the loop and away from the loop, in both the cases he is observing the deflection in the galvanometer. Okay, so next what he has done is he kept the magnet here, and then he started moving the loop up and down. So in that case also he observed the deflection in the galvanometer. So whether you move the magnet nearer to the loop and away from the loop, in that case he observed the deflection in the galvanometer. Now if you kept the magnet stationary and if you move the loop up and down, in that case also he has observed the deflection in the galvanometer. Now he started moving both magnet and loop relative to one another. In that case also he observed the deflection in the galvanometer. Understood? Okay, so in all these cases he observed the deflection in the galvanometer. So whenever this loop and magnet both are stationary Understood? So in that case he has not observed any deflection in the galvanometer. So whenever this loop and magnet both are stationary, both are not moving with respect to one another, in that case he has not observed any deflection in the galvanometer. So whenever this magnet is moving or this loop is moving or both are moving, in that case only he has observed the deflection in the galvanometer. So that means what he concluded is whenever there exists a relative motion between the loop and the magnet, only in that case we are seeing the deflection in the galvanometer. If there is no relative motion between the magnet and loop, in that case we are not seeing any deflection in the galvanometer. Right? Okay, so these are the observations he has made here. So what is his observation here? So whenever there is a relative motion, relative motion between what? Between magnet and loop here. Whenever there is a relative motion between magnet and loop, in this case he observed a deflection. In what? In galvanometer. He observed a deflection in galvanometer. Right? Okay, so whenever there is no relative motion here, whenever there is no relative motion between magnet and loop, whenever there is no relative motion between magnet and loop, in this case there is no deflection, deflection in galvanometer. So this is what he has observed. Right? Okay. So if there is a deflection in galvanometer, means what here? There is a deflection in galvanometer means what? So there is some induced current flowing in the loop. there is an induced current flowing in the loop, and hence the galvanometer is showing some deflection. Understood? Okay. So now what is causing this deflection in galvanometer? That is nothing but a relative motion between magnet and loop. Relative motion between magnet and loop. So what actually happening whenever there is a relative motion between magnet and loop? So what is happening actually whenever there is a relative motion between magnet and loop? See here, see whenever you keep the magnet here and loop here, so these field lines, these magnetic field lines are penetrating through this surface here. Yes or no? The magnetic field lines are penetrating through this surface that is enclosed by this closed loop. Or I can say simply, these magnetic field lines are penetrating through this loop. Understood? Okay. So the number of field lines, the number of magnetic field lines that are penetrating through this loop, or the number of magnetic field lines that are penetrating through this surface, both mean same here. Okay. Penetrating through this surface, we call it as what here? We call it as a magnetic flux. We call it as a magnetic flux. Right? Okay. So what do you mean by magnetic flux here? The number of magnetic field lines that are penetrating through the loop. Or I can say the number of magnetic field lines that are penetrating through this surface that is enclosed by this loop. Both mean same, right? Okay. So now what happens to this magnetic flux? What happens to this magnetic flux whenever there exists a relative motion between magnet and loop? See here, if you move the magnet, away from the loop here, if you move the magnet away from the loop, then what will happen here? The number of field lines that are penetrating through this loop is going to decrease with respect to time. So the number of field lines, the number of magnetic field lines that are going to penetrate through this loop are going to decrease with respect to time as the magnet moves away from the loop. So that means what here? The number of field lines are decreasing with respect to time means what? The magnetic flux is decreasing. Magnetic flux is decreasing. So whenever the magnetic flux is decreasing, there is a deflection in the galvanometer. Understood? Now in the similar manner, if you move the magnet in upward direction, then what will happen here? So if you move the magnet in upward direction, that is nearer to the loop, then what will happen? The number of field lines that are penetrating through the loop is going to increase with respect to time. So that means the magnetic flux through the loop is going to increase with respect to time. So in this case also, he has observed the deflection in the galvanometer. Understood? Okay. So that means, see here. So that means, see here. So this is the loop and this is the galvanometer, right? Okay. This is the galvanometer. So whenever the magnet is moving away from the loop here, what happens to the field lines here? Okay, so the number of field lines that are penetrating through the loop are going to decrease as the magnet moves away from the loop. So that means in this case, what is happening here? Magnetic flux is decreasing. Yes or no? Magnetic flux is decreasing. Okay, magnetic flux through the loop is decreasing. Understood? Okay. So next, if you consider the loop, okay, or I'll draw here. Okay, so I am considering the loop here, right? So I am considering the loop. So to the ends of the loop, I have connected here a galvanometer, right? Okay. Now in this case, let us say the magnet is moving towards the loop. The magnet is moving towards the loop. So it is moving like this. So in this case, what will happen here? So the number of magnetic field lines, that are penetrating okay, so the number of field lines that are going to penetrate through the loop is going to increase as the magnet moves towards the loop. right? Okay, so here the magnetic flux, so in this case the magnetic flux is decreasing. In this case magnetic flux is what? Is increasing. The magnetic flux is increasing, right? Okay, so the same is the case if you move the loop, if you keep the magnet stationary and if you move the loop up and down, in that case also you are going to have what? You are going to have a change in magnetic flux. That means there may be an increase in magnetic flux or there may be a decrease in magnetic flux. If the loop moves away from the magnet, then there will be a decrease in magnetic flux. If the loop moves towards the magnet, then in that case the magnetic flux is going to increase. Understood? Okay, so in this manner, whenever the magnetic flux is decreasing and whenever the magnetic flux is increasing, you are seeing the deflection in the galvanometer. So this is what happening whenever there is a relative motion, between the magnet and loop. So what is happening here? Whenever there is a relative motion between the magnet and loop, there is a change in what? There is a change in magnetic flux. Understood? Okay, so whenever there is a change in magnetic flux, you are seeing the deflection in the galvanometer. So that means there is an induced current. Flowing through what? Flowing through the conductor. And hence galvanometer is showing some deflection. Understood? And one more thing here, what is causing this current? See, why the current? See, we know that if the current is flowing inside the conductor, means the charge carriers are going to flow in a particular direction around the wire. Yes or no? The charge carriers inside the conducting material are going to flow in a particular direction around the wire. That is what is called as what? That is what is called as current. So that means all the charge carriers are moving in a particular direction. So there must be some force. That is going to drive the charge carriers inside the conducting material to flow in a particular direction. Understood? So what is that force driving these charge carriers inside the conducting material here? That is nothing but what? That is nothing but EMF. Yes or no? Okay, so that means whenever there is a change in magnetic flux, there induces an EMF around the closed loop, and this induced EMF is causing or driving the currents inside the conductor. Understood? Okay, so what is the conclusion we can make here? Whenever there is a relative motion between magnet and loop, there will be a change in magnetic flux. Whenever there is a change in magnetic flux, there induces an EMF around the closed loop, and this induced EMF is going to cause what? Is going to cause the induced current within the loop. Understood? Okay, so this is the conclusion he has made here. Understood? Okay, so that means finally he concluded that if you are having only magnetic field, it is not going to produce any current, but there is a change in magnetic flux. If you are having a change in magnetic flux, then it is going to cause what? Then it is going to cause the current. So this is what he has concluded. Okay, so only if you are having B field, a stationary B field, then it is not going to produce any current. So what must be present? There must be a change in magnetic flux. So then you can see a current. A change in magnetic flux can produce what? Can produce the current. Why it is producing current? Because there induces an EMF around the closed loop, and that EMF is causing what? Is causing this current. Understood? Okay, so these are the conclusions he has made here. Okay, so now we try to give the mathematical form here. To this Faraday's law. Okay, so now see here, I am representing this magnetic flux. With what? With phi b. So whenever there is a change in magnetic flux, that means dou phi b by dou t. So whenever there is a change in magnetic flux, so what he has observed here, there induces an EMF around the closed loop. Understood? Okay, so whenever there is a change in magnetic flux, there induces an EMF around the closed loop. So here we have put we are going to put some minus sign here. Here we will put some minus sign. So what is the purpose of this minus sign here? This minus sign is because of what? This minus sign is because of Lenz's law. Lenz's law. Okay, so we will discuss about this Lenz's law later. Understood? Okay, so first we will concentrate on this equation. So that is induced EMF around any closed loop is equivalent to what? Is equivalent to the change in magnetic flux. That means whenever there is a change in magnetic flux, there induces an EMF around the closed loop, and here we are putting minus sign. This minus sign is because of what? Lenz law. We will study about this Lenz law later. As we proceed into the subject, we will study this Lenz law also. Right? Okay. Okay. Just here we are trying to give what? We are trying to give the mathematical form to Faraday's law. That's it. Right? Okay. Okay. So now, now see here. So this is the EMF. This is the EMF induced around the closed loop. This is the EMF induced around the closed loop. So how we can represent the induced EMF in terms of what? In terms of electric field. See, while dealing with electrostatics here, we have seen this expression here, that is closed loop line integral E bar dot dl bar. So in electrostatics, while dealing with electrostatics here, we have seen that the closed loop line integral E bar dot dl bar, or the circulation of electric field around any closed loop, is always equal to what? Is always equal to 0 in case of what? In case of electrostatics. So there I have told that this equation represents what here? This equation will represent KVL. So why this equation represents KVL? Why I have told that? Because here the units of electric field is nothing but volt per meter, and the units of this differential length is also nothing but what? Meter. Now here meter will get cancelled, so it represents what? It represents the voltage around what? Around any closed loop. Okay, so the summation of voltages around any closed loop is equal to what? Is equal to 0, which is called as what? Which is called as KVL. Okay, so this is what we have studied in electrostatics. So that means the closed loop line integral E bar dot dl will represent what here? Will represent the voltage around what? The voltage around what? Around a closed loop. Understood? Okay, so that means this VEMF here, this induced EMF, we can represent in terms of what? In terms of electric field. How we can represent here? So EMF, the voltage around any, this is nothing but what? Voltage around any closed loop. Yes or no? This is the voltage induced around any closed loop, right? Okay, so how we can represent voltage around any closed loop? Just now I have told. Okay, so in terms of electric field, I can represent this as a circulation of electric field around any closed loop. So in this manner I can represent induced EMF. Now in time varying case here, we are dealing with what? Now we are dealing with what? We are dealing with time varying fields. Yes or no? Okay, so here the circulation of electric field around any closed loop is not equal to 0. Here we got, in electrostatics we got it as equal to 0. Here we are not going to get equal to 0. So this is equivalent to what? This is equivalent to minus dou by dou t into what? Into phi b. So the circulation of electric field around any closed loop is equivalent to what? Is equivalent to the time rate of change of magnetic flux. Understood? So whenever there is a change in magnetic flux, there induces an EMF around that closed loop. So the induced EMF around the closed loop is nothing but what? Is nothing but the circulation of electric field around any closed loop. Both mean what? Both mean same. EMF induced around closed loop is same as what? Is same as the circulation of electric field around any closed loop. So this is what you have to understand, right? Okay, so now this phi b is nothing but what? This phi b is nothing but magnetic flux. So that means the number of magnetic field lines that are penetrating through a loop. So how we can represent this phi b here? See here, I am considering here. So here I am considering a closed loop here. Right? Okay. Some closed loop here. I am considering some closed loop here. Right? So some closed loop. Or we will take we have connected galvanometer here. Okay. So we will take that loop only. Right? Okay. Now here, if you are having the magnet here, so this is north pole, this is south pole, so the number of magnetic field lines that are penetrating through this loop, the number of magnetic field lines that are penetrating through this loop, we call it as what here? Magnetic flux, right? Okay, so now see here, so if I consider a small differential area dA bar here, if I consider a small differential area dA bar on this surface here, so this is the loop here, this is the loop, and this loop is enclosing what? This loop is enclosing this surface, and the number of field lines that are penetrating through this surface is called as what? Magnetic flux. Understood? Okay, so now on this surface, over this surface, I have considered a small differential area dA bar. Now, if you want to determine how much of the magnetic field that is penetrating through this small differential area dA bar, then how to represent that here? How to represent that? How to represent the field penetrating through any surface? We have done it many number of times. Yes or no? Okay, so the magnetic flux or the number of field lines that are penetrating through this small differential area dA bar, I can represent it as what? I can represent it as simply B bar dot what? B bar dot dA bar. B bar dot dA bar. Now, if I want to determine the total number of field lines that are penetrating throughout this surface here, then what you have to do? You have to integrate throughout this surface that is enclosed by this loop. Yes or no? You have to integrate throughout this surface. So if you integrate throughout this surface, then you are going to get the total number of magnetic field lines that are penetrating through this surface, or I can simply say the magnetic flux through this surface. Understood? So this is the representation of what? This is the representation of magnetic flux. This is the representation of magnetic flux. Right? Okay. Now just substitute here. In place of phi b, just substitute double integral b bar dot dA bar. Just we are trying to give the mathematical representation of Faraday's law. Right? Okay. Okay. So you have to observe how we are developing this mathematical representation and all. We have learned the concept. Okay. So then we are developing what? We are developing its mathematical representation also. Right? Okay. So now see here. So this expression, I can write it as what here? I can write it as the circulation of electric field. The circulation of electric field around any closed loop is equal to what? Is equal to minus dou by dou t. Phi b is nothing but what? Phi b is equivalent to double integral b bar dot dA bar. This is the magnetic flux. Yes or no? This is the representation of magnetic flux. So just substitute that. So double integral b bar dot what? B bar dot dA bar. So this is nothing but what? This is nothing but phi b. Understood? Okay. Okay, yeah. Okay. Fine. Right. So the same thing here, the same expression I can represent in this manner. See here, the circulation of electric field around any closed loop is equal to what? Is equal to minus of what? Minus of double integral. I am sending this dou by dou t inside the integration. So then I can represent the same thing as dou b bar by dou t dot what? Dot dA bar. So in this manner also I can represent. Yes or no here? Yes or no? So why here? Why? Here dou by dou t, that means this differentiation is with respect to what? With respect to time. Here we are doing what? Integration. So this integration we are doing with respect to what? With respect to space. So integration is spatial operation here, and the differentiation is a time operation. So we know that this time operation and spatial operation both are what? Both are independent to one another. So that means you can perform first spatial operation, then after that you can perform the time operation, or you can perform first time operation, then you can perform what? Spatial operation. The result is not going to change, because the spatial operation and the time operation both are what? Both are independent to one another. Okay, so and hence you can represent either in this manner or in this manner. It doesn't matter. Both are going to be what? Both are going to be correct only. Right? Okay, so we landed up with the final form, the final mathematical form of what? Of Faraday's law. So this mathematical form is in terms of what? In terms of integrals. So we call it as what? We call it as a integral form here. So you can represent in this manner or you can represent in this manner. It doesn't matter. Okay. It is also called as what? Either this one or this one. Both are called as what? Integral form of what? Faraday's law. So this we call it as a integral form of what? Integral form of Faraday's law. Integral form of Faraday's law. Right? Okay. So this is called as integral form of Faraday's law. So if you want to, you can replace in place of B bar. So where B bar is equal to what? Where B bar is equal to mu into what? Mu into H bar. So if you want, you can represent in terms of what? In terms of mu into H bar also. So here you can write in place of B bar, you can write mu into H bar. So you can take mu outside since it is a constant. It is constant, mu is constant with respect to time as well as space. So you can take it out of these operations and you can write simply dou H bar by dou T dot dA. Here you have to write mu. So in any manner you can write here, it's your wish, right? Okay, okay. So this is the integral form. This is the integral form of Faraday's law, right? Okay. Now, now for this LHS side here, for this LHS side, I am considering this LHS side. So for this LHS side, I am applying what here? I am applying I am applying Stokes theorem here. I am applying Stokes theorem to this LHS side. So we know that by applying Stokes theorem, we can convert the closed loop line integral into what? Into surface integral. Yes or no? Okay. So by applying Stokes theorem, I can represent this LHS side as a double integral curl of what? Curl of E bar dot what? Dot dA bar. So this is equal to what? This is equal to minus of double integral dou B bar by dou T dot what? Dot dA bar. Understood? Okay. Okay, yeah. So here so by comparing LHS to RHS, okay, what you are going to get? Del cross E bar is equal to what? Is equal to minus dou B bar by dou T. Or you can say the surface integral on LHS side and the surface integral on RHS side, both represents what? Both represents the same surface. Okay, so that means the surface integration on both sides will get what? Will get cancelled. So finally we'll land up with what? We'll land up with the differential form. Finally we land up with the differential form or point form of what? Point form of Faraday's law. So that is curl of E bar is equal to what? Is equal to minus dou B bar by what? Dou B bar by dou T. Dou B bar by dou T. Understood? Okay. So this is the point form or differential form. So this is called as point form. This is called as a point form or a differential form. Point form or a differential form. Point form or differential form of what? Of Faraday's law. Right? Okay. So this is the integral form of Faraday's law, and this is the point form or differential form of what? Point form or differential form of Faraday's law. Okay. Okay, see, we can get the intuitive feeling of Faraday's law in the integral form only here. So here you can easily understand. Understood? Okay, so here in the integral form we can easily understand the Faraday's law. You can get the intuitive feeling what this Faraday's law is saying. Understood? But it is very difficult to visualize this one in terms of what? In terms of point form or differential form. Here I can tell curl of E bar. Curl of E bar represents what? Represents the circulation of electric field about a given point is equivalent to the time rate of change of magnetic field at that point. I can tell it as a statement, but you don't get that intuitive feeling, right? Okay, so it is very difficult to visualize this point form or differential form. Understood? Okay, so rather we got this form from this integral form only. Right? Okay, so this is the main concept. If you understand the concept here, from this same concept only, we have just represented the same thing in terms of what? In other form. That's it. Okay, the concept is not going to change, right? Okay, so this is the point form or differential form of Faraday's law, and this is the integral form of Faraday's law. Understood? So in order to get the intuitive feeling of Faraday's law, you have to understand what this integral form mean, right? Okay. Okay. So finally we got a integral form of Faraday's law. So that is the circulation of electric field around any closed loop is equal to what? Is equal to minus dou by dou T double integral B bar dot dA bar, right? Okay, so and the point form or differential form is curl of E bar is equal to what? Is equal to minus dou B bar by dou T. So these are the point form and differential form and integral form, right? Okay, so this is the integral form. This is the point form or a differential form of Faraday's law, right? Okay. Okay, right. Okay. So this is what we got here, that is integral form or point form or differential form of what? Faraday's law. So these are the mathematical forms of what? These are the mathematical forms of Faraday's law, right? Okay. So now again coming to our basic equation here, our basic equation. So that is this one here. See here. See the voltage induced around any closed loop, the voltage induced around any closed loop, right? So we got this expression, that is the voltage induced around any closed loop is equal to what? Is equal to minus dou phi b by dou t. So this is the basic equation we have written. So from this we have derived what? We have derived or we have expressed the same thing in terms of what? Integral form, and we have expressed the same thing in terms of what? In terms of point form or differential form, right? Okay. 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 So Parasmun, what you are asking here, why are we using E bar dot dl in magnetic field? We are not using E bar dot dl bar here. Why we are using here? This is E bar dot dl bar represents what? E bar dot dl bar represents the EMF induced around any closed loop. Yes or no? So we have observed that whenever there is a change in magnetic flux, there induces an EMF around the closed loop, and that EMF is causing the induced current in the loop. Understood? So from where we are getting EMF, this is nothing but what? EMF is nothing but what? EMF is nothing but voltage induced around the closed loop. So the voltage induced around the closed loop you can represent in terms of what? In terms of electric field. Yes or no? Without electric field there is no voltage here, right? Okay. So this EMF induced we can represent in terms of what? In terms of electric field in this manner. Understood? So already I have explained this thing, how to represent the voltage around any closed loop in electrostatics here. There I have explained already this thing. Understood? Okay. So the voltage around any closed loop, here we are getting equal to 0, which we call it as what? KVL. So here the voltage induced around any closed loop is not equal to 0. Here it is equivalent to what? It is equivalent to the change in magnetic flux through that loop. Understood? Okay. So that's what you have to understand here, right? Okay. Okay. Right. So now coming to the basic equation here, coming to the basic expression. So that is VEMF, that is induced voltage. So this is equivalent to what? This is equivalent to this is equivalent to what? Minus dou phi b by what? Dou phi b by dou t. Dou phi b by dou t. Right? Okay. Okay. Right. Dou phi b by dou t. So here I have told that this minus sign is because of what? Yeah, this minus sign I have told that this is because of Lenz's law, right? So I have told that this minus sign is because of what? Is because of Lenz's law, right? Okay. So now we will see what is this Lenz's law. We will see what is this Lenz's law, right? Okay. So right. So what is the purpose of Lenz's law here is with the help of Lenz's law here, we can determine the direction of the induced current. See here, whenever there is a change in magnetic flux, we know that there will be an induced current because of induced EMF, right? Okay, but we don't know the exact direction here. So we know that whenever the flux is increasing, there will be an induced current around the loop in one direction, and whenever the flux is decreasing, in that case there will be an induced current flowing in the loop in another direction, but we don't know exactly in which direction here. So in order to identify the exact direction of the flow of current in the loop, we will take the help of what? We will take the help of Lenz's law. We will take the help of Lenz's law. Understood? So now I will explain what is this Lenz's law. What is this Lenz's law, right? Okay, see here. So Lenz's law here, Lenz's law. So we know that whenever we are having a cause and effect, whenever we are having cause and effect, right? So whenever we are having cause and effect, right? So this effect will always opposes what here? The effect will always opposes what? Opposes cause. Yes or no? So that is what is Lenz's law. So what Lenz's law says here? You are going to have cause as well as what? Its effect. So this effect is always going to oppose the cause, always going to oppose the cause, right? Okay, okay here. Now here, what is the cause here? What is the cause here? So the cause is nothing but the change in what? Change in magnetic flux, the change in magnetic flux. Okay, so M flux means magnetic flux here, right? So cause here is nothing but change in magnetic flux. So whenever there is a change in magnetic flux, what is the effect we have observed here? What is the effect we have observed? So that is there induces an EMF around the closed loop. There induces an EMF around the closed loop, right? Okay, so whenever there induces an EMF around the closed loop, there flows what? There flows an induced current, So this electromotive force is going to drive the charge carriers within the loop, that is going to result in the induced current, right? Okay, so whenever you are having an induced current, we know that whenever there is a current, it is going to produce what? It is going to produce magnetic field. Yes or no here? So whenever you are having here induced current, so this induced current is going to produce what? Is going to produce induced magnetic field. Induced magnetic field. We call this field as what here? Induced magnetic field. Understood? Okay. So now this is the final effect here. This is the final result, right? Okay. So this effect has to oppose what? Has to oppose the cause. Yes or no? So that means this induced magnetic field, this is the final effect. So this effect has to oppose what? Has to oppose this cause. So this induced magnetic field has to oppose this change in, what? This change in magnetic flux. Understood? So here I have told here change in magnetic flux. So what do you mean by change here? What do you mean by change? So it may be what? It may be increase in magnetic flux, yes or no? Or it may be what? Or it may be a decrease. In magnetic flux. Change in magnetic flux means it may be increase in magnetic flux, or it may be what? Decrease in magnetic flux. So here from Lenz's law, what we can conclude here is whenever there is an increase in magnetic flux here, then this induced magnetic field will try to oppose this increase in magnetic flux, will try to oppose this increase. Understood? Okay. And similarly, whenever this magnetic flux tries to decrease, this induced magnetic field will try to oppose that decrease here, decrease in magnetic flux. Understood? So always it is going to oppose the change. Induced magnetic field is going to oppose the change in magnetic flux. So if it is trying to increase, then it is going to oppose that increase. In the same manner, if it is trying to decrease, then it is going to oppose that decrease. Understood? Okay, so this is nothing but Lenz's law here. So now what I have told here, what is the application of Lenz's law I have told? So the purpose of Lenz's law is we can specifically determine the direction of what? The direction of the induced current around the closed loop. Understood? Okay, so how we can determine? See here. How we can determine that? See here. Okay, so based on this, there are many conceptual questions they have asked in exams. Okay, not only in GATE here, in GATE I think they have not asked it. Okay, but in IAS and in other competitive exams, we can see many number of questions which is based on what? Which is based on this Lenz's law. right? Okay, okay, yeah. Now see here, I am considering the loop here, I am considering some loop here, I am considering some closed loop here. Understood? Okay. Now now let us say the magnet, here I am considering the magnet. Okay, so let us assume this magnet is moving, towards what? Towards the loop. Okay, so whenever the magnet is moving towards the loop, what happens here? The number of field lines, that are penetrating through this loop are going to what? Are going to increase with respect to time. Yes or no here? So the number of field lines that are penetrating through this loop, are going to increase with respect to time. So here what I am assuming, the magnet is moving towards the loop. So whenever it is moving towards the loop, the magnetic flux through this loop, or the magnetic flux through this surface, is going to what? Is going to increase. Yes or no here? Why? The number of field lines that are penetrating through this surface is increasing gradually as the magnet moves nearer to the loop. Understood? So that means here in this case the magnetic flux, is increasing. Why you are saying magnetic flux is increasing here? Because with respect to time, the number of field lines that are penetrating through this loop or through this surface is increasing. That's why you are saying magnetic flux is increasing. Understood? So whenever the magnetic flux is increasing, this induced magnetic field has to oppose this increase in magnetic flux. Yes or no? This induced magnetic field will try to oppose this increase in magnetic flux. So that means the number of field lines, penetrating through this loop are increasing with respect to time. Now the induced magnetic field will try to oppose this increase, So that means in which direction the induced magnetic field must be present here? See, if the induced magnetic field is pointing in upward direction, let us assume if the induced magnetic field points in upward direction, then it is aiding what? Then it is aiding the increase in magnetic field. Yes or no? But here it has to oppose what? It has to oppose the number of field lines that are penetrating through this surface. It has to oppose the increase in number of field lines that are penetrating through this surface. Okay, so how it can oppose here? So in that case, in which direction the induced magnetic field must point here? It has to point in downward direction. Yes or no here? The induced magnetic field has to point in which direction? The induced magnetic field has to point in downward direction. Understood? Okay, so why here the induced magnetic field is opposing what? We'll try to oppose the increase in magnetic flux. So in that case, the induced magnetic field has to point in which direction? The induced magnetic field has to point in downward direction. Understood? Okay, so if the induced magnetic field is pointing in downward direction, then what must be the direction of the induced current here? So if the induced magnetic field is pointing in downward direction, means the induced current will flow in which direction? It is going to flow in clockwise direction. Yes or no? Okay, so here the induced current through the loop is going to flow in which direction? It has to flow in clockwise direction. Understood? So that means finally what is happening here is, whenever there is an increase in magnetic flux, that means with respect to time, the number of field lines that are penetrating through the loop is increasing. Okay, so the induced magnetic field will try to oppose that increase. So that means the induced magnetic field has to point in downward direction. So if it is pointing in downward direction, means the induced current through the loop must flow in which direction? Must flow in clockwise direction. So if it flows in clockwise direction, then only it is going to produce the induced magnetic field in downward direction. So which means it is opposing what? It is opposing the increase in number of field lines with respect to time, or I can say it is opposing the increase in magnetic flux. Understood? Okay, yeah. Now similarly, if I consider the loop, I am considering the loop here, right? Okay, so I am considering some loop here. So I am considering the loop here, right? So now let us assume the magnet is moving away from the loop. Now the magnet is moving away from what? Away from the loop, away from the loop, right? So whenever it is moving away from the loop here, so what will happen here? So the number of field lines, the number of field lines that are penetrating through this loop, the number of field lines that are penetrating through this loop are going to what? Are going to decrease, are going to decrease. Okay, so as the magnet moves away from the loop, then the number of field lines that are penetrating through this loop is going to decrease with respect to time. Okay, so this I can say here, the magnetic flux is what? Is decreasing. The magnetic flux is decreasing. Okay, so that means the number of field lines that are penetrating through this loop is gradually decreasing with respect to time. So now what this induced magnetic field will do here? The induced magnetic field will try to oppose what? Will try to oppose this decrease in magnetic flux. Decrease in magnetic flux. So decrease in magnetic flux means with respect to time, the number of field lines that are penetrating through this loop are decreasing. So the induced magnetic field will point in a direction such that it tries to oppose this decrease. It tries to oppose this decrease. So that means now in which direction this induced magnetic field must point here? Tell me, in which direction it must point? Whether it has to point in upward direction or it has to point in downward direction? Tell me here. Okay, so there is no one to tell the answer, right? Okay. So whenever the number of field lines that are penetrating through this loop are decreasing, then the induced magnetic field will try to what? Will try to oppose this decrease, So that means in which direction it has to point here? Now the induced magnetic field has to point in which direction? It has to point in upward direction. Yes or no? Because the number of field lines that are penetrating through the loop is decreasing with respect to time, and hence the induced magnetic field will try to oppose this decrease. That means it has to point in which direction? It has to point in upward direction. It has to point in upward direction. Okay, so in this case, the induced magnetic field is going to point in upward direction. So the induced magnetic field, this is the induced magnetic field, has to point in upward direction. So if the induced magnetic field is pointing in upward direction, then what is the direction of the induced current here? The direction of the induced current must be in which direction? It must be in anti-clockwise direction. Understood? So in this case, the induced current through the loop will be in anti-clockwise direction. Understood? Okay. So that means with the help of Lenz's law, okay, so what we have determined here? We have determined the specific direction of what? Specific direction of the induced current. Understood? Okay, so here we have seen that the current is flowing in which direction here? The current is flowing in anti-clockwise direction. Thus it is going to produce the induced magnetic field in downward direction, so that it is opposing the increase in magnetic flux. Always you have to see the change here. What is the change? Whether it is increasing or decreasing. Okay, so based on that you are going to decide the direction of what? Decide the direction of induced magnetic field. Okay, so here the number of field lines penetrating through the loop with respect to time is increasing, so the induced magnetic field will point in a direction such that it will try to oppose this increase. So that means induced magnetic field will point in downward direction and the induced current will flow in clockwise direction. So here the number of field lines that are penetrating through the loop is decreasing with respect to time, and the induced magnetic field will try to oppose the decrease. So that means it has to point in which direction? Upward direction. So in this case, the induced current will flow in which direction? Anti-clockwise direction. Understood? Okay, so this is what you have to understand here. So this is nothing but what? This is nothing but Lenz's law. So with the help of Lenz's law, we can determine the exact direction of the flow of currents. Okay, so directly based on this one here, this concept. Okay, so they have asked many questions in different examinations here, right? Okay, yeah. So we have understood this Lenz's law also. So that means we have understood this Faraday's law completely, right? So whenever there is a change in magnetic flux, this induces an EMF around the closed loop, and here we will put minus. This minus sign is because of what? Is because of Lenz's law, right? Okay, okay. So this is the basic concept here. This is the basic concept of Faraday's law here. This is the basic concept of Faraday's law, right? Okay, okay. Okay. So here from these two what we can observe here is, so from this Lenz's law here, okay, so what we can observe here is whenever the number of field lines that are penetrating through the loop are increasing, okay, so this is the direction of B field, yes or no? This is the direction of B field. So this B field I am calling it as actual B field here. So this is B actual, so I am calling this as B actual, right? Okay, so I am calling this B field, the B field produced by what? This magnet, understood? So this is the actual B field. So and this green color, whatever I have represented in green color, this is nothing but induced magnetic field. So this B field I am calling it as actual B field. This is the actual B field, okay, and this is the induced magnetic field. Now see here, what we can observe from these two means, see here, so whenever the magnetic flux is increasing here, that means whenever the number of field lines that are penetrating through the loop is increasing, okay, so then if you observe the direction of B actual, I am talking about direction now, okay, so the direction of B actual is pointing in upward direction, and the induced magnetic field is pointing in downward direction. So that means in this case the direction of B induced is exactly opposite to what? Is exactly opposite to B actual. Understood? Okay, this is the observation we can make from here. Okay, so from here, what is the observation we can make here? Here, if you observe here, B actual, okay, B actual is pointing, still it is pointing in which direction? Upward direction. I am talking about the direction here. Okay, still it is pointing in which direction? Upward direction. Understood? Okay, so now here, what is the direction of induced magnetic field here? The induced magnetic field is also in upward direction. Understood? So that means whenever the magnetic flux is decreasing here, the direction of induced magnetic field will be along what? Will be along the direction of what? Will be along the direction of actual magnetic field. Yes or no? Okay, so that means here, okay, see here. So here a direction of B induced is the direction of B induced is along what? Is along or is same as what? Is the same as B actual. Understood? Okay, so these are the observations we can make here. So if you make these observations here, then whatever the problem they will give, you can easily identify the direction of the induced magnetic field, and you can from that you can easily get the direction of what? The direction of induced current. Understood? So what are the conclusions we can make here? So whenever the direction of induced magnetic field, whenever the magnetic flux, so whenever the magnetic flux is increasing, in that case, the direction of induced magnetic field is exactly opposite to what? Is exactly opposite to the direction of what? The direction of actual B field. Understood? And here, whenever the magnetic flux is decreasing, so in this case, the direction of induced magnetic field is along or same as what? Same as B actual. I am talking about directions here. Remember that. Understood? Okay. Okay. Yeah. So these are the conclusions we can make. So Animesh Singh, what you are asking here, sir, is 5G really harmful? I too don't know that here, right? Okay. So I think it is irrelevant to this subject, I think so, right? That means whatever the topic we are studying now, so for that topic it is irrelevant, right? Venkatesh Gopal, understood, sir. Okay, fine. Okay. So now see here. Now I will give you some questions here. You have to tell me the answer. So Venkatesh Gopal, you have understood now. Okay. So Parasmoon, I think you also understood, right? Okay. So now I will give one simple questions here based on this Lenz law. You have to tell me the answer, right? Okay. Okay. Now see here. If I consider the loop, right, or otherwise okay. So I am considering the loop like this. So here what I am doing here is I am so this is the magnet here, this is the magnet, right? Okay. So this is the magnet, right? Okay. So this is a north pole, or I will take other side. I will do like this here. See here, I am taking the magnet here. Let us say this is the magnet, right? Okay. So let us say this is north pole and this is south pole. So it is moving towards what? Towards the loop. Okay. So let us consider this is position 1. So it is moving towards what? Towards the loop. Right. Okay. Next, it has crossed the loop here. Now here, so whenever it crosses the loop, then here on this side, so it is moving like this here. It is moving downwards. It has crossed the loop. Now it is moving like this. Okay. So here what you are going to have? Here you are going to have south pole and here you are going to have north pole. So now it is moving away from what? It is moving away from the loop. So this is the second situation. Okay. So in the first case, the magnet is moving towards the loop, and in the second case, the magnet is moving away from the loop. Okay. So in the first case, tell me what is the direction of induced current? So that means whether it is clockwise or anti-clockwise. And in the second case, tell me what is the direction of the induced current, whether it is clockwise or anti-clockwise. That's what I am asking, right? Okay. Tell me. Just we are applying that Lenz law. You have to know how to apply the Lenz law, right? Okay. So now tell me here. So Venkatesh Gopal, Parasmoon, if you are there in online, please let me know the directions of induced current in case 1 and in case 2. So the magnet is moving towards the loop like this, and it is moving here away from the loop here. Okay. So now I am asking the direction of the induced current. So in order to know the direction of the induced current, first of all you have to know the direction of induced magnetic field. Understood? Okay. Okay. Do it here. So whenever the magnet is moving towards the loop, in this case, the number of field lines that are penetrating through the loop is going to increase, right? Okay. The flux linked increases, yes. As the magnet moves towards the loop, the magnetic flux is going to increase. Okay, so now what is the direction of the induced magnetic field? The induced magnetic field will try to oppose what? Will try to oppose the increase in magnetic flux. So that means what must be the direction of the induced magnetic field? So if you know the direction of the induced magnetic field, then you can determine the direction of the induced current. Okay, so direction of induced current means I am asking whether it is clockwise or anti-clockwise Okay, that's what I am asking here. Whether the current through the loop is clockwise or anti-clockwise. So here also I am asking whether it is clockwise or anti-clockwise. So that's what I am asking. Just analyze here, just analyze. I have given each and every clue here. I have given each and every clue here also. So I have given that whenever the flux is trying to increase, the induced magnetic field direction will be opposite to what? Opposite to actual magnetic field direction. Whenever the flux is decreasing, the direction of the induced magnetic field will be along what? Will be along the direction of the actual magnetic field. Okay, if you know the direction of induced magnetic field, then you can easily tell the direction of what? Induced current, right? Okay, so I am expecting some answer from you guys, right? Right, tell me here. Okay, see here. Listen here, listen Venkatesh, listen. See here, we know that always the field lines are going to leave what? Are going to leave the north pole, and they are going to enter at what? They are going to enter at the south pole. Yes or no? So whenever the magnet is moving nearer to the loop, what will happen here? See, the magnetic field lines are going to leave what? Are going to leave the north pole. Are going to leave the north pole. So that means the magnetic field lines will be what? Will be like this, right? Okay, so the magnetic field lines are going to penetrate through the loop like this. Now as the magnet is moving towards the loop, this magnetic flux is what? This magnetic flux is increasing. Right? So we know that whenever the magnetic flux is increasing, the direction of the induced magnetic field must be opposite to what? Must be opposite to the direction of what? Actual magnetic field. So this is B actual. Right? Okay. So now the induced magnetic field must be what? Must be opposite to what? Must be opposite to the induced magnetic field. The induced magnetic field must be opposite to what? Must be opposite to what? Must be opposite to actual magnetic field. So when it is opposite to actual magnetic field, that means induced magnetic field has to point in upward direction. So if the induced magnetic field is pointing in upward direction, then what is the direction of induced current? The direction of induced current will be in anti-clockwise direction. So here the I induced will be what? Will be in anti-clockwise direction. So in this case, for case 1 here, the induced current will be in which direction? Anti-clockwise direction. Okay, so now here I am drawing this second one separately here. Okay, see here, second case. So here you are having the loop, and now the magnet is moving away from the loop. Right? So whenever it is moving away from the loop, here you are having south pole and here you are having north pole, right? Okay, we know that always the field lines will point, the field lines will point towards what? Towards the south pole. The field lines will point towards the south pole, right? Okay, so the field lines will point what? Will point towards the south pole. So whenever the magnet, this is the second case here, this is the second case, this case. Okay, so whenever the magnet is moving away from the loop, whenever the magnet is moving away from the loop, the number of field lines that are penetrating through this loop are going to what? Are going to decrease, are going to decrease. So that means here the magnetic flux, here in this case the magnetic flux is what? Is decreasing. Yes or no? The magnetic flux is decreasing, right? So just now we have told that whenever the magnetic flux is decreasing, whenever the magnetic flux is decreasing, the direction of induced magnetic field will be along what? Will be along the direction of what? The direction of actual magnetic field. So here this is B actual, yes or no? This is the direction of what? This is the direction of actual magnetic field. The direction of actual magnetic field is pointing downward direction. So that means here the induced magnetic field, the induced magnetic field must also point in which direction? Must also point in downward direction. So if the induced magnetic field is pointing in downward direction, then what must be the direction of induced current here? It has to point in which direction? Clockwise direction, right? Okay, so it has to point in clockwise direction. It has to flow in clockwise direction. So this is the direction of induced current. So in this manner, you have to identify the direction of the induced current. Okay, okay. So if you if you analyze in this manner, then whatever may be the problem, whatever may be the conceptual question that is based on Lenz's law, you can easily answer here, right? Okay, okay. So I hope it is crystal clear, right? Okay. So I hope it is clear, Venkatesh, right? Parasmoon, I think this one, second case and first case, both are clear, I hope so, right? Okay. So if you are having any doubts, you can ask me. Right? Okay. So is this clear? Basiraju Lokesh, clear sir. Okay, right? Okay. So now I will take one more example here. I am expecting the answers from every one of you here, whoever watching. Okay, I am expecting the answers from every one of you. Okay, so now let us consider. I am considering the magnet. Let us consider this is the magnet here. This is the magnet, right? So here I am considering north pole, and here I am considering, here I am considering south pole, here I am considering north pole, right? So let us assume this magnet is moving. Let us assume this magnet is moving towards the loop in this case, towards the loop. So let us consider this is first case, right? Okay. So now here the magnet has crossed this loop, and now it is moving like this. So that means here you are going to see north pole, and here you are going to see south pole. So the magnet is moving like this. So this is second case, right? Okay. So now tell me, what is the direction of the induced current? Okay, so if it is flowing in this direction here, if it is flowing in this direction, then it will be what? Anti-clockwise direction. If it is flowing like this, then it is anti-clockwise direction. If it is flowing like this, then you have to say clockwise direction. Understood? Okay, so tell me the answer here. Tell me the answer. In first case, what is the direction of the induced current? In first case, what is the direction of the induced current? And in the second case, what is the direction of the induced current? Tell me. Tell me here. In first case, what is the direction of the induced current? And in the second case, what is the direction of the induced current? Tell me. So first case clockwise. So Venkatesh has given in the first case, he has said that induced current will be in clockwise. We will check here, we will check that, right? Okay. So whether it is clockwise or anti-clockwise, we will check that. He has given clockwise, right? For the second case here, for the second case, what you got? For the second case, what you got? Okay, he is saying again, he has changed his answer here. He is saying it is a anti-clockwise direction. For first case, he is saying anti-clockwise direction, right? Okay, no problem. Okay, so here you are getting anti-clockwise, right? Here, what is the direction of induced current? See, whether it is correct or wrong, it doesn't matter here. Just try this one here. Try it. Try it and tell me the answer. Right. Okay. So now we will check here. We will check whether this answer is correct or wrong. See here. So whenever the magnet is moving towards the loop, whenever the magnet is moving towards the loop, here we are having south pole here. South pole means the field lines are going to move what? Will be towards what? Towards the south pole. Towards the south pole. Right. The field lines will be towards the south pole. So this is B actual. This is B actual. Right. Okay. So whenever the magnet is moving towards the loop here, whenever the magnet is moving towards the loop, then the number of field lines that are penetrating through this loop is going to increase. Yes or no? So that means in this case, the magnetic flux is what? Magnetic flux is increasing. The magnetic flux is increasing. Right. Okay. So whenever the magnetic flux is increasing here, whenever the magnetic flux is increasing, so what I have told here, the direction of induced magnetic field must be what? Must be opposite to the direction of what? Must be opposite to the direction of the actual magnetic field. Understood? So actual magnetic field is pointing in this direction. So that means induced magnetic field must point opposite to what? Opposite to this actual magnetic field direction. So if the induced magnetic field is pointing in this direction, means the current has to flow. The current has to flow in which direction? It has to flow in anti-clockwise direction. Okay. So whatever Venkatesh said is correct here. Is correct. Right. Okay. So it must be in anti-clockwise direction. Very good here. Very good. Okay. Next, in the second case here, for the second case, I am drawing here separately. For the second case, I am drawing here separately. Okay. So this is the loop I have given. Now the magnet is moving. The magnet is moving away from the loop. Okay. So whenever it is moving away from the loop, here you are going to have what? Here you are going to have south pole, and here you are going to have north pole. So it is moving away from the loop. So we know that the number of field lines, the field lines are going to leave what? Are going to leave the north pole. Right. Okay. So the field lines are going to leave the north pole. Right. Now here, as the magnet is moving away from the loop, the number of field lines that are penetrating through this loop are going to decrease with respect to time. So that means in this case, magnetic flux. So this is second case here. This is second case. Okay. So here the magnetic flux is what? Magnetic flux is decreasing. Magnetic flux is what? Magnetic flux is decreasing. So whenever the magnetic flux is decreasing, what is the direction of the induced magnetic field here? The direction of the induced magnetic field must be along what? Must be along the direction of the actual magnetic field. So here this is nothing but what? This is nothing but B actual. This is nothing but B actual. right? Okay, so the direction of B actual is pointing in this direction. So here the induced magnetic field must point in the same direction. So that is B induced. Okay, so if it is pointing in this direction, then what is the direction of induced current? The direction of induced current must be in clockwise direction, right? Okay, so it must be clockwise direction. So this is the induced current direction. Okay. Okay, Parasmun, second one, how you are getting? Second one is clockwise, right? For second case, what we are getting here? Induced current direction will be in which direction? Will be in clockwise direction. For the first case, it is what? Anti-clockwise direction. For the first case, it is not clockwise, Parasmun. It is anti-clockwise, right? Okay. See, here the flux is increasing. So whenever the flux is increasing, the direction of induced magnetic field must be exactly opposite to what? Must be opposite to the actual magnetic field direction. So the actual magnetic field direction is pointing in this direction. So the induced magnetic field has to point in this direction. If the induced magnetic field is pointing in this direction, then the induced current has to flow in anti-clockwise direction. Okay, so this is the induced current here. So this is for the first case. Understood? And this is for the second case. Right? Okay. So here the magnet is moving towards the loop. It crosses the loop and it is moving away from the loop here. So in both the cases, in the first case, in the second case, we try to determine the direction of what? Direction of the induced current. Understood? Okay. So these are the applications of what? This is the application of Lenz's law. So with the help of Lenz's law, we can determine the exact direction of the induced current. Right? Okay. So I hope it is crystal clear. Right? Okay. So with this here, with this I am winding up the session for today. Right? So before coming to the tomorrow's class, please revise all these things here. Please revise whatever I have told in Faraday's law. Please revise all those things, right? Okay, so then you will feel comfortable whenever we are doing the applications of Faraday's law, right? So tomorrow we will see the applications of what? Applications of Faraday's law. So we'll try to solve some more problems based on Lenz's law, and also we try to solve some problems based on what? Faraday's law. So we'll see different applications of Faraday's law here, right? Okay. So please, before coming to the next class, please revise all these things so that you will feel familiar or comfortable while doing the applications, while learning the applications of Faraday's law. Understood? Okay. So tomorrow we will meet exactly at what? Tomorrow we will meet exactly at 4 p.m. Yeah. Tomorrow we will meet exactly at 4 p.m. Okay. So stay safe and keep learning here, right? Okay. So everybody stay safe and keep learning, right? Stay safe and keep learning. So take care here, take care all of you. So we will meet exactly at 4 p.m. tomorrow, right? Okay. So okay, so stay safe and keep learning. So tomorrow exactly at 4 p.m. we are going to meet, right? So until then, take care. Bye bye. So wait here, wait. Parasmoon, what you are saying here, your answer is wrong. Which one here? Which one is wrong? Parasmoon, can you tell me which one is wrong here? You should not say simply wrong here, you have to explain, right? So you have to tell where I have done wrong. Tell me where I have done wrong here. Tell me. The field lines always moves towards what? Will point always towards what? Towards the south pole. Yes or no? So this is the direction of what? This is the direction of the actual B field. This is the direction of the actual B field. So whenever you are moving the magnet nearer to the loop, what is happening? The number of field lines that are penetrating through this loop are increasing. So that means the magnetic flux is increasing. So if the magnetic flux is increasing, the direction of induced magnetic field must oppose what? Must oppose the direction of actual magnetic field. So the direction of actual magnetic field is pointing in this direction, that is from left to right. So the induced magnetic field direction must point from where to where? From right to left. So if it is pointing from right to left, that means if it is pointing in this direction, means the induced current must flow in which direction? It has to flow in anti-clockwise direction, right? Okay, so in that what is wrong here? In that what is wrong? I don't understand what you are saying, right? Okay. Okay, and in this case, in the second case, so the magnet is crossed the loop and it is moving away from the loop. So in this case, what is happening here? So the B actual is pointing in this direction. As the magnet moves away from the loop, the magnetic flux is decreasing. So whenever there is a magnetic flux decreasing, then what will happen? Here? The direction of the induced magnetic field must point what? Must point along the direction of what? Must point along the direction of actual magnetic field. So that means it has to point in this direction. So if it is pointing in this direction, then what is the direction of the induced current? The direction of the induced current will be in which direction? Will be in clockwise direction. So for first case, it will be what? It will be in anti-clockwise direction, and for the second case, it must be in what? Clockwise direction. So both, how you will get clockwise here, right? Whenever it is moving towards the loop, flux is increasing, and whenever it is moving away from the loop, the flux is decreasing. In both the cases, how you are going to get the same, right? Parasmoon, tell me here. You just simply post a question and then you don't give any response, right? Okay. How you are saying my answer is wrong here? How you are saying that? You should not post simply something like that here, right? With the explanation you have to tell. I am saying now why it is anti-clockwise, why it is clockwise, all those things I am saying or not, right? Okay. Okay. So if you are not having any proper explanation for that, okay, so don't comment like that here, don't do like that, right? So if I have done any mistake, represent that, sir, you have done somewhere mistake, so this is the problem, this is the wrong, or calculation is wrong, okay, or something this is wrong. So like that you can express, right? Okay. So after all these explanations, you are saying simply I am wrong. Okay, what does it mean? I don't understand. Okay, yeah. Okay, anyway, I don't mind, right? Okay, yeah. So tomorrow exactly at 4 p.m. we are going to meet. So stay safe at home and keep learning. So we'll meet tomorrow exactly at 4 p.m. So until then, take care. Bye bye.